Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. What if the powerful lens of a telescope, or even your glasses, could be as thin as a sheet of paper? And what if you could adjust that flat lens electronically to zoom or change focus instantly, with no moving parts? This sounds like magic, but scientists are making rapid strides toward exactly that: flat, adjustable optics. Recently, a major breakthrough brought us closer to replacing bulky curved lenses with metalenses, flat surfaces etched with tiny nanostructures that manipulate light. And not only are they flat, the latest ones can be dynamically tuned. This could revolutionize everything from smartphone cameras and medical imaging to the eyes of future spacecraft. Let's dive into how they achieve this and what it means for technology and exploration. Traditional lenses versus metalenses. Why go flat? Traditional lenses, like those in cameras, telescopes, or even our eyes, rely on a curved shape to bend light rays and focus them. They work great, but they have some downsides. They tend to be thick and heavy if you need a lot of focusing power. Think of telephoto camera lenses or observatory telescopes, big hunks of glass. They also have limitations like spherical aberration and need complex shapes or multiple elements to correct. Now consider a metalens. Instead of a curved glass, imagine a flat piece of material. Could be glass, plastic, or even a semiconductor, with a pattern of millions of nano-sized antennas or pillars on its surface. These nanostructures interact with incoming light waves in a carefully designed way, so that by the time light passes through, it's focused or shaped just as a normal lens would do, but without the bulk. Essentially, the heavy lifting of bending light is done by the tiny pattern, not by a macro-scale curvature. This concept has been around for a bit, and labs have made metalenses that can do things like focus light or form images, often using materials like titanium dioxide or other nanofabricated patterns. They promise ultra-thin optics. Your future phone camera might not need a protruding lens bump if it had a flat lens, for example. Well, for example, satellites could have lighter imaging systems, important for launch weight. Even eyeglasses could potentially be just a sliver of material, but correct vision perfectly. However, until now, metalenses had a key limitation. Once you fabricate that nanostructure pattern, it's fixed. A normal lens can't change its shape either, unless it's some special mechanical zoom or using liquid lenses. So most metalenses were static. One focal length, one function. If you wanted it to do something else, you needed a different pattern or some external mechanism. There have been experimental tunable metalenses, but performance was often low. The breakthrough here, achieved by a team at Linköping University in Sweden, uses a clever approach to make metalenses that are adjustable after fabrication. The breakthrough, using conductive plastics for tunable flat optics. The researchers work with conductive polymers, which are plastics that can conduct electricity and also have interesting optical properties. A few years back, the same team showed that by using a conducting polymer as the material for the nano antennae on a metalens, they could electrically switch the lens on and off. Conductive polymers can change their state when you apply a voltage. Essentially, they can go from transparent to reflective or change refractive index by oxidizing or reducing. Adding or removing electrons causes a chemical change. Think of it like a plastic that can act like a metal when charged and go back to a less metallic state when not. In 2019, they demonstrated the concept of an active metasurface using such materials. You could modulate the optical effect, albeit modestly. The problem was their performance wasn't as good as, say, a gold or dielectric like TO metasurface in terms of focusing efficiency or clarity. The new research has improved the performance tenfold, bringing these polymer-based metasurfaces much closer to the efficiency of the best traditional ones. They achieve this by extremely precise nanoscale patterning, placing the polymer nanostructures in just the right arrangement to capture and focus light much more effectively. Essentially, they overcame a lot of the optical losses. The result: a flat lens made of a conductive plastic that can, for example, focus light strongly and can be electrically tuned. Tuning could mean turning the focusing effect on off, or even shifting the focus distance. Imagine a sheet that one moment doesn't focus at all, acting like just a window, and the next moment, with a small voltage, it becomes a magnifying lens, or a lens that can toggle between focusing at 10 centimeter versus 20 centimeter away. That kind of flexibility in one piece of flat tech is unprecedented. Future applications, from holograms to space telescopes, holograms to space telescopes. The researchers themselves mention things like video holograms, invisibility materials, sensors, and biomedical imaging as possible uses. Let's explore a few scenarios to understand the impact. Augmented reality and holograms. A dynamic metasurface could project holographic images by steering light. If it's fast enough, you could create true holographic video displays, something companies and sci-fi have long dreamed of. Instead of bulky optics, you might have a thin visor or a sheet-like device generating 3D images in midair by focusing and diffracting light in precise ways. Smart glasses or camera lenses. Glasses with flat lenses that can auto-adjust focus would be amazing. For instance, as people age, focusing at different distances, near versus far, becomes an issue. Presbyopia. Imagine glasses that sense where you're trying to look and electronically adjust the lens pattern so you always see clearly at any distance, all with a thin lens that doesn't look any different from regular glasses. Similarly, a smartphone camera could have a flat lens that zooms or changes focus length with no moving parts. Just electrical signals, making cameras more robust and potentially giving better image quality in a small form factor. Invisibility or adaptive camouflage. The term invisibility materials basically refers to cloaking, bending light around an object. Tunable metasurfaces could potentially redirect light on the fly. While true invisibility cloaks for visible light are extremely challenging, we might get surfaces that can adaptively minimize reflections or control exactly how something is seen. Perhaps a spacecraft skin that can modulate its thermal emission or optical signature to avoid detection or to manage heat, which leads to space applications. Think about satellite optics. Traditional satellites with large lenses or mirrors, like Hubble or James Webb, are feats of engineering and require deployment in space. Webb's folding mirror, etc. In the far future, one could imagine large, very lightweight flat lens arrays made by printing these metasurfaces on thin films. They might be easier to fold and deploy than glass mirrors. There's research into diffractive space optics. This fits right in. Also, a flat lens doesn't have to be rigid. You could potentially have a flexible lens sheet that rolls out. If it can also adjust focus, so one telescope could do multiple tasks, wide angle and zoom, for example, just by tuning the lens. For smaller satellite cameras, weight and space are at a premium, so metalenses could allow high-resolution imaging in a much tinier package, important for CubeSats or planetary probes. Biomedical imaging. In medical devices like endoscopes or microscopes, you often want small optics you can insert in the body or on a chip. Flat lenses can shrink those systems. A dynamically tunable lens could, switch between different depths of focus in a microscope instantly, or help An endoscope camera focuses on tissues at varying distances without mechanical movement. Useful in a tiny pill camera, for instance. Optical sensors and LiDAR. In autonomous cars or drones, having flat, tunable optics could simplify LiDAR systems, which currently often use mechanical scanners or phased arrays. A metasurface could steer a laser beam just by electronic control, making solid-state LiDAR that's even more compact. For space robotics or habitats, LiDAR is used for navigation and mapping. Smaller, more versatile optical elements there would be beneficial too. This breakthrough is a major step, but it's worth noting, it's probably still in the lab stage. We'll need to see it scaled up in size and manufactured reliably. But the fact that they improved performance by 10x suggests we're getting closer to practical viability. Closing thought. The notion of flat optics is transforming our centuries-old understanding of lenses. Since the time of Galileo's telescopes or the first spectacles, we assumed lenses had to be curved pieces of glass. Now we're on the cusp of a paradigm shift where a lens could be a flat tech component, as thin as a wafer, potentially as programmable as a computer chip. It's like turning optics into a form of software-defined hardware. Change the code, voltage pattern, and change the function. It sparks the imagination. How will this change the design of future devices we use every day, or the instruments we send across the solar system? Will the bulky camera lenses of today become relics, replaced by elegant flat patches on our devices? And philosophically, it's intriguing. We've learned to sculpt and control light with nanostructures smaller than the wavelength of light itself, essentially teaching light new tricks on a tiny stage. But as this technology matures, we might see a world where our interaction with visual information is far more dynamic and immersive, from true holographic projections to invisibility cloaks. It's a reminder that even something as classic as a lens can be reinvented in the age of nanotech. The next time you look through a pair of glasses or snap a photo, consider that the future of those lenses might be flat, smart, and almost science-fictional in capability. How will that change the way we see our universe and ourselves?